Swayam Prabha. Digital India. Educated India.
Tell me what is a monodentate ligand and what is a bidentate ligand. Example? Halogen. What is halogen? Chlorine or chloride? And what is a bidentate ligand? For example, oxalate. What is a bidentate ligand? For example, dry structure. Ethylene diamine, oxalate. Monodentate ligand means ligand which can bind to metal using one atom, and bidentate utilizes two atoms. The simple example is ammonia and ethylene diamine. This is a monodentate ligand, right? That's a bidentate ligand. If I do like that's a tridentate ligand, right? Three atoms are coordinated, tridentate ligand. This one polydentate or tetradentate. This one, the previous one tetradentate. This one, count. The previous one tetradentate, this also tetradentate, but there is a difference. What is the difference? This is tetradentate but cyclic. If this is not there, also tetradentate, but not cyclic, acyclic. What is the difference between 2 ammonia and ethylene diamine? This we call a chelating ligand, bidentate chelating ligand. Okay. Is this a bidentate ligand? What it is called? Bipyridyl or dipyridyl. Like ethylene diamine. This part is like ethylene diamine. This is also a bidentate ligand or chelating bidentate ligand. Is this a bidentate ligand? What it is? Monodentate. but there are two nitrogen. Monodent. What is the meaning of monodentate? Which one? This one or that one? Any one. What happened to the other one then? If this is connected to metal, can this connect to a metal? Can it connect to metal? Not the same metal. It cannot connect to the same metal. So, this is a chelating bidentate ligand and this one is a non-chelating bidentate ligand. Still it is bidentate, but it's a non-chelating bidentate ligand, or you can also call it bridging ligand. Bridging ligand means it bridges two metal. So, chelating bidentate, non-chelating bidentate. Monodentate, bidentate, tri-tetradentate. Within tetradentate, I show that it can be either cyclic or not cyclic. Where it is cyclic, this is the one. When it is not cyclic, there are many chelate rings. How many? 3. 1, 2, 3. And here 1, 2, 3, 4. Number of chelate ring is 3, number of chelate ring is 4. At the same time, this is cyclic and that is not cyclic. Okay. So, how much of this thing was known to you? Or known but you could not bring it together in one place? Because when I ask, you are looking a little blank, not so confident. So, ligand can be monodentate, bidentate, tridentate, polydentate. It can be chelating, not chelating, cyclic, not cyclic, and so on. Okay. When you say metal and ligand, generally what kind of metal comes to your mind? Tungsten metal ion, right? Copper, nickel, cobalt, this kind of thing. Whether sodium comes to your mind? It doesn't. Copper, nickel is usual. But if I say sodium and a ligand, then it sounds, what are you telling? Right? Sounds a little strange. Do you know that in our body there is a lot of sodium ion, potassium ion? And it is transported from one place to another place. So who is doing that thing? That is the ligand. How it will go? It has to bind, transport and release. So how it will bind? By some interaction, right? If it is sodium chloride, we do not say chloride is bound to sodium. In solid state, yes. But once you put sodium chloride in water, what happens? Na plus Cl minus dissociate. So around sodium, what is there? In water, put sodium chloride, dissociate to Na plus and Cl minus. Around Na plus, anything is bound or nothing is bound? Oxygen is bound. Water. Okay, that is called hydration. Do you know hydration? When water associates with something, that is called hydrogen. In that process, if the energy is released, then that's a feasible thing. So when Na plus is in water, it is surrounded by water molecule, where Na plus is coordinated by oxygen. Okay. So that is also a metal complex. But you never thought about it. Complex of sodium ion. When you say potassium ferrocyanide, K4 FeCN6, you put iron, you put cyanide, you put a square bracket, and you say potassium, that you stay outside. As if that one is not important for metal complex formation, right? And that remain like a K plus 4 times. So it's dissociated. So we generally talk about transition metal as the metal ion when you say metal complex, right? what do you expect here? If you take phenol and Rx, X is a leaving group. Phenol react with Rx in presence of a base. What is the job of the base? Deprotonate phenol become O minus. O minus attack, Rx minus goes out. This is a very simple typical reaction, right? There is nothing to explain here. It's a simple reaction in organic chemistry. Okay. One to dihydroxy benzene. What I showed earlier is monohydroxy benzene or phenol. Dihydroxy benzene. If dihydroxy benzene react with Rx, what will happen? OR and OR. Two places now. Okay. If I want to prepare this thing, then what do I do? If I put Rx to this compound, 1,2-dihydroxybenzene, then it can react at one place or this both are equal. If it react at only one of the OH, whether reacts here, same thing. And if it reacts at both places, then two possible compounds, right? Is it possible to get only that compound? How? By? If you are telling something, finish the sentence. Okay, do you know the deprotection technique? If we can somehow protect one side, okay, by using some protecting, there are some techniques, then one side is protected, other is available. Then you react. After the reaction is over, deprotect. That is called deprotection technique, right? Let's say PG for protecting group. Okay. If you react this one with Rx, then that compound will form after deprotection, right? Oxygen at the center, CH2X. It's like Rx now. If we react this compound with that compound, it can react here, it can also react here. Or if we have two equivalents, let's say something like this. In presence of a base, we should be possible to prepare after reacting in presence of a base, then doing deprotection, it should be possible to prepare that compound. So somebody targeted to prepare that compound by starting from here, then protecting, then reacting with this one in presence of a base followed by deprotecting it, targeting that compound. Okay. So if you have a phenol, one is phenol having a H, one is ether, no H, but a alkyl group or something. The UV visible spectrum of this compound, you know what is UV visible spectrum? What it is? What is UV and what is visible? And visible, right? When we irradiate a substance with light, it may absorb, it may not absorb. If it doesn't absorb, all light comes out. And if it absorbs, then the intensity of the light is lower, right? So in UV visual spectrum, you get something like this. Okay? If it doesn't absorb, how much it absorbs? The amount of absorption is this much. And here, no absorption. And that's your wavelength, right? And this is that intensity of absorption. This bigger height means at that wavelength, light is absorbed. How much it is absorbed? And if it is like this, means at that wavelength, all light comes out. Okay? So when you take phenol, it absorbs around 275 nanometer. Phenolic compound absorbs around 275 nanometer. If we add some base to this compound, then the peak shifts to little bit higher wavelength in presence of sodium hydroxide. It goes to the higher wavelength and intensity also increases. This is the general observation. And if we have a compound like this, that will absorb around 275 nanometer, but if we add sodium hydroxide, there will be no change. Okay? So, keep that thing in mind. So, during this process of preparation, the target was to prepare a metal complex a pentadentate ligand a metal complex was targeted. Whatever that metal may be, don't worry about it. And in that process, this should be major product. But he got some minor product as well. At this stage, this is major plus some minor product also, and who was making it, while isolating the major product, he got the small amount of minor product, and he was also interested in the minor product because it was looking very attractive to him. Crystalline, sharp crystalline kind of thing, intensely dazzling, silky white kind of thing. So he got interested in knowing what is that minor product. So he isolated the minor product, yield may be very, very small, and that minor product he subjected to this kind of test. What test? UV visible spectroscopy. And he found that there is a peak around 275 nanometer. Then he put some base there. There is no increase in wavelength and increase in intensity, means OH is not there. Okay? So the minor product, OH is not there. If OH is not there, then fine. But instead, it showed another peak, like the peak got splitted. If it is OR, there should be no change. If it is OH, there should be change. in intensity as well as wavelength. But there was no change in wavelength and there was a splitting pattern there in presence of sodium hydroxide and potassium hydroxide. Then it was not possible to know what has happened. If we get a compound like this, there should be change in wavelength, or if this is protected, because protecting group was used, then there should be no change. But something else, so neither it is protected nor it is deprotected. What could be that thing? So that was not known at that point of time. After a lot of research, he found out what has happened. This compound, although it is protected, it's a different kind of compound now. It's a cyclic compound. And how it is possible? In case this one is not completely protected, there is some minor amount of suppose in the process of protection, when protecting group is given, this one should form. Along with that, there is something which is not protected. If not protected, then the product will be in between the protected thing forms, right? So one more can react here. Are you understanding? This one is protected. His initial intention to prepare something like this, then undergo deprotection. But there itself, something were OH, hence instead of having the protecting group, one more equivalent of this reacted there. Are you able to follow? So that the cyclic compound is formed. That's how he somehow proved it, that it formed a cyclic compound. And that cyclic compound gives this kind of behavior because in the center of this, it binds sodium ion inside the cavity. So it's a cyclic ligand which binds sodium ion. Okay. And this happened in the year 1967. In the year 1967, this was prepared. And slowly it was observed that the kind of compound, now it's called a ether, right? Oxygen, both side carbon, it's a ether compound. We can say a cyclic ether compound or cyclic polyether compound. This compound could bind Na plus ion or K plus ion. If we take sodium or potassium salt, put in water, it is soluble. If you put in organic solvent, it's not soluble. It's not soluble. In water, it is soluble. If you put sodium chloride in ethanol, toluene, benzene, it's not soluble. But he found that the polyether, cyclic ether, is soluble in organic compound. And if you put sodium salt or potassium salt there, it becomes soluble. So who helps in the solubilization? That cyclic compound. By capturing the sodium or potassium ion inside the cavity, it solubilizes that. So that's a new finding now. Solubilization of sodium salt in organic solvent. And this begins the coordination chemistry of S block element. Sodium ion, potassium ion, S block element. Their coordination chemistry started from that point of time in a coordination chemistry type of research. As I already told at the beginning, sodium ion, potassium ion, they are present in biological system. They are complexed by valinomycin. Binds this thing. If you study bioinorganic chemistry, you will find Na plus K plus that can be bound by different kind of biosystems for transporting, for example, valinomycin. You can check by yourself. So, have you heard the name crown ether? In what context? In green chemistry. Okay, what is crown ether? Do you know the structure? Can you draw? So that means if I do not have the benzene ring here, that's what you are trying. That is called crown ether. This is also crown ether. This is called benzo. This is one more benzo, so dibenzo crown ether. Or little bit better way of telling is, if you count the number of atoms in the ring without counting that part, then it will be 18. 6 oxygen and 2 carbon. Like that, if you see, this also counts as 2 carbon. Then total there are 12. 12 plus 6, 18. So this is called dibenzo 18 crown 6. Dibenzo to say 2 benzo, 18 to say there are 18 atoms in the ring, crown is the name given, and 6 is 6 number of oxygen atoms. So that's how the dibenzo crown ether 6 was prepared for the first time, which binds sodium ion and potassium ion. So that means if you do not do this step of protection, directly take OH and treat there, then the chances of getting the crown ether will be higher and the yield will also be better, right? Then what you have to do is take 1,2-dihydroxybenzene, bis chloroethyl ether and a base. It was found that when the base is sodium hydroxide or potassium hydroxide, yield is good. When it is a lithium hydroxide, yield is not good. When it is a ammonium hydroxide, yield is not good. So that means it's not only OH minus, the deprotection of the OH or deprotonation of the OH, it's also something else is there. If only deprotonation of OH has to be the reason for the reaction, then sodium hydroxide and lithium hydroxide should work equally. But lithium hydroxide did not give good yield. So that means in the process of formation, it is necessary to have something which will bind here. And why that? That we will discuss now. Do you know what is a polymer? Monomer. For example, ethylene, polyethylene, right? If we react these two compounds in presence of a base, then can it not continue like that? It can continue like that. And that would be a polymer. But the polymer is not formed, or if formed, it is in less amount. Why should the polymer not form? In order to form the polymer, this has to extend and go like that. In order to form a cycle, this has to come back like that. If it comes back, then only it will form cyclic. If it doesn't come back, it will go to polymer. When one molecule and one molecule reacts, this is formed, right? When the second molecule reacts, either it will react here, maybe this will react here, or it may also react here. Two possibilities. In that process, If it is a long one, then it will keep on growing to form a polymer. And when it will not be polymer? Let's say it formed like this and it turned the way I have drawn. And why should it turn? Somebody has to hold it and turn, and that somebody is Na plus or K plus ion, which is having some kind of electrostatic interaction to hold it in that turn position, either this way, otherwise it's also a possibility, right? Before the closure happens, it's also a possibility. If it forms in this way, then it's trying to put in a particular shape where by further reacting with this require dihydroxybenzene and this require chloroethyl ether to close the ring. And who is holding it in that format? The potassium ion or sodium ion. In fact, when this one reacts, this can also start forming interaction. This can also start forming interaction before it can actually react to bring them closer. That is called a template. Template is something around which the molecule orient in a particular format to go to the cyclic form. If the template is not there, if sodium or potassium ion is not there, lithium is little too small. The size of lithium is smaller than sodium and potassium. So when it is small, it may not be able to hold them, it will just come out. Whatever is the overall size of the ring which is going to form, if the metal ion fits there, then that's a better thing. Tight fit is there, then it holds better. So sodium and potassium ion fits better to that ring size, hence the yield is better. If lithium hydroxide is put or ammonium hydroxide is put, hydroxide is able to make deprotonation of phenol, but holding that linear thing which is trying to polymerize is not possible by ammonium or lithium that well. So sodium and potassium gives better yield. So that's how it was found that not only the OH minus, also the metal ion has the role as a template. Okay. So this compound is called crown ether, that is called dibenzo 18 crown 6. If benzene is not there, that is called 18 crown 6. It's a cyclic molecule. Can you see now? Oxygen, CH2, CH2, then again oxygen, CH2, CH2, oxygen, like that. And why it is called crown? Because it's like a crown, right? That's why it's called crown. If you want, you can put on your head and take a photograph. It's called crown, like whenever they say have different competition, Miss World, the crown, right? Likewise. So the person who prepared, he wanted to put the name crown ether. Otherwise, if you want to give IUPAC nomenclature to such a compound, it will be extremely difficult. It will be too lengthy, and you have more and more compound, nomenclature will be difficult. So he devised a shorthand nomenclature, called it crown ether system. And the oxygen atoms in almost in one plane, and the potassium or sodium is somewhere here. It binds like that. Since I am holding like that and drawing like that, you are having a feeling that this is a cyclic planar compound. But it can be like this also, right? Why should it be cyclic? Why should it be planar? It could be anything. The conformation, if you remember, carbon-carbon bond, eclipse, staggered, gouge, those things are there. This one, what I put is eclipse, is it not? When it's eclipse, it's not good, energetically not favorable. If it is like this, it will be good for them, right? Or like that, somewhat like this, if you do, that will be good. But still, even though you change the conformation, they are not going away from the molecule, they are part of the molecule. If you have ammonia, 6 number of ammonia around a metal, or if you have 3 number of ethylene diamine, stability increases. If you have 2 units of diethylene triamine, stability further increases because the number of kilotring increases. Here, that is the case. In ethylene diamine 2 nitrogen, they cannot go away from each other. They can be somewhere around moving, but cannot be completely departed. Likewise, here all the 6 oxygen, they has to be rotating here and there, but cannot go away from each other. So this is called chelate effect, which is known to you. In addition to chelate effect, there is another effect which is called macrocyclic effect. This is called a macrocycle, a cyclic compound called macrocyclic compound, not just cyclic. If you say, if I ask you, give example of a cyclic compound, you will not say crown ether. You may say cyclohexane, right? If you do not think about crown ether, don't know about crown ether, then example of a cyclic compound is obviously cyclohexane. Hence, calling this thing a cyclic compound is not a good idea. Because I may have a cyclohexane here, right? So that is not cyclic, this is called macrocyclic. In macrocyclic, there should be at least 9 atoms, then it's called macrocyclic by definition. So the crown ether, when it binds to potassium or sodium, that time it will be this conformation. When it is not bound, it could be something else. Or during the synthesis, if template is present here, then it will try to orient in this way. If the template is removed, then it can go to some other conformation, right? Okay, so if we have 6 oxygen, then it should be possible to have somehow, by some means, more than 6 oxygen or less than 6 oxygen also. If there are 6 oxygen, we say 18 crown 6. If there are 5 oxygen, it is called 15 crown 5. If there are 7 oxygen, it is called 21 crown 7 and so on. So people have prepared different kind of crown ethers. The 4 oxygen, 5 oxygen, 6 oxygen, even 9, 10, 12, so many oxygens are prepared. But it was found that mostly for the purpose of this work, the 6 is best. Hence, 18 crown 6. That's there most of the places. And who prepared this compound? His name is, do you know? No? Pedersen. Charles J. Pedersen. Charles J. Pedersen. And he was working in a company as a chemist after MSc, not PhD. After MSc, he was a research scientist. After his retirement, he did lot of good work for the company. So after retirement, he said that I want to do something which may not be of interest to the company. Then because he was loyal to the company, he worked so much. So they say, okay, you do whatever you want to do, don't bother us. Whatever chemical you want to purchase, we'll allow you, but you do by yourself. Do not take our help. Then he tried to prepare that complex IC metal complex with half cycle kind of thing. To do some catalysis work, he started to make that thing. In the process, he got small amount of compound, which he analyzed, and ultimately crown ether chemistry started because of him at that point of time, who was retired and having no interest in the company's thing. And this was also not his intended work by chance. If you would not have taken that small amount of compound and analyzed and tried to study, then he would not have prepared crown ether, possibly somebody else at some other point of time, but not at that point of time. And if it is delayed, it could have been much delayed also, who knows. So that's how the crown ether started. In 1967 he prepared, and he prepared several other crown ethers, tried to study different kind of binding of alkali metal ion and so on. Then he stopped working because he was quite old. And as I told you, he was just a MSc, not even PhD. Later on, after several more years, in the year 1987 he got Nobel Prize in chemistry because of this crown ether chemistry what he started. In addition to some other people did some other work. So that time when the Nobel Prize was awarded, he was not forgotten. He was very old. He never imagined that he would make to Nobel Prize. How he would think that just making a cyclic compound by simply adding dihydroxybenzene and bischloroethyl ether and binding sodium, how should that go to Nobel Prize? But it went. Okay, so now you have some idea about what is crown ether, how it started, and it binds alkali metal ion, which is not the usual metal ion when you talk about coordination chemistry. And the relevance of this thing is to this biosystem where sodium ion, potassium ion transport is there. Right? Okay. Have a look if you want. Look it and keep transferring. Draw this by yourself. I want to see how you are drawing. So far you are just watching the movie kind of thing. Draw this compound. Do not get afraid. It looks so huge, but look at the symmetry. It's a symmetrical compound. Try to draw and see that you are drawing almost a circular kind of thing, cyclic kind of thing. Those who make rangoli outside the house, what it is called, kolam or something. If you do that thing, it will be easy for you. It's a molecular column. Okay. And if you are able to do now, then you will be also able to do column if you have not done before. They are related. Okay. So, many oxygen, many carbons. I draw the same thing once again. So, this is about the story of an old man who was retired from his job at the age of 60 something. He did by curiosity research and got something and he stopped doing. That time, a young professor just started his career after finishing his PhD and other thing in France. This was in America, USA, in a company called DuPont. He was working. And the second one, what I am talking about now, is another very young professor who just started his work. He thought, what happened instead of oxygen if I take nitrogen? Okay. If its oxygen valence is 2, nitrogen valence is 3. So, if it is nitrogen, can I do like this? Right? From nitrogen, keep drawing the similar kind of thing again. Okay? So, this compound is called crown ether. Do you have any idea what it is called? No. Aja crown ether is the compound where simply make it nitrogen, that become aja crown ether. When one more arm is added, that is called cryptant. It's called cryptant. What is the difference between the crown ether and cryptant? In crown ether, it is a monocyclic compound. 2-dimensional, you can say, a ring kind of thing. And that one is a 3-dimensional compound. Okay. If it is 3-dimensional compound, if potassium ion is inside the cavity, is protected from all the three sides. In the cyclic compound, potassium is there at the center, is protected in one plane. From top and bottom, it's open, right? And in that way, if it's nitrogen valency 3, it's a kind of tetrahedral or trigonal pyramidal, you can say. So in that way, there will be three arms, which is 120 degrees away from each other. So all the three directions, it will hold it. So keeping that in mind, we prepare to bind potassium ion inside the cavity in this way, binding potassium ion inside the three-dimensional cavity. For that also I have something for you. Now you have a look. If you do not look at one of the arms, the other two arms are not planar cyclic. It's slightly bent. So approximately in 3 points, from 1 point, 3 point has come out, and 3 arms are hanging down. You see one of the arm, nitrogen, CH2, CH2O, CH2, CH2O, CH2, CH2N. Earlier that was oxygen in the crown ether. And from here, the other thing which was going in the same plane, now it is either that side or it is this side, because 3 things has to be attached. So in this way, you see, so all oxygens are now pointing inside in a 3-dimensional way it will cover. So this will have much better binding ability for the potassium ion. The look is entirely different now. That one looking like a ring, this looks like a 3-dimensional elliptical object. Pass it on. So it's called crown ether, that is called cryptont. Have you heard of supramolecular chemistry? Supramolecular chemistry, anybody? In the CSR UGC syllabus chemistry, have you seen what is there? Inorganic chemistry, organic chemistry, physical chemistry, and at the end there are some 4 topics, which is interdisciplinary kind of thing. One of that topic is supramolecular chemistry. And what I am teaching now is supramolecular chemistry. Okay. I doubt whether you will be taught this thing in your MSc wherever you are or not. But if you are interested in getting another 1 or 2 mark in CSIR, if you learn this thing, study by yourself, this may help. If that question comes. If it doesn't come, don't blame me. In supramolecular chemistry, molecular chemistry versus supramolecular chemistry. What is supramolecule and what is a molecule? What is a molecule? Group of atoms forming a molecule. A molecule is a molecule, right? It's difficult to define what is a molecule, but you understand what is a molecule. Think like that. In supramolecular, the interaction between molecule is considered. Molecule interact with another molecule or few more molecule is called supramolecular. Take a break. 3 o'clock. Take a break of 5 minutes, then again one more. Start now? Okay. Okay, so in this diagram, let's say this is 1,2-dihydroxybenzene, the arrow tip is OH, which attacks. One more unit of 1,2-dihydroxybenzene. This one is bis-chloroethyl ether, where the arrow attacks. So I put in this way. This one attacks here, forms a bond. Okay. Instead of drawing the structure, I just draw lines. It's understood what is what. Let's say A is one molecule, B is another molecule. The chances of their collision is higher if they are nearby, and it becomes lower if they are further. And how to make them nearby or how to make them further? If you have a solvent, reactants are in the solvent. If we increase the amount of solvent, then the molecules are separated from each other. Hence, their chance of collision is lower. Reactivity will be lower. Chance of collision lower means, of course, reactivity is lower. Let's say this one reacts 1 and 1. After that, bond is formed here. Okay. So the next one comes, let's say here, and the way I am putting is instead, what happens if it comes like that? If it comes here, it closes the ring. Even though template is there, still instead of going here, one side can go here and one can go there, and it happens like that, it will be polymeric. The chance of this one meeting to that one is higher when they are closer. So if you put more and more amount of solvent, then things are separated. So once this one attaches here, finding another if this one is further away, then finding this point and this point together, chance is lower. Therefore, it can turn like that. And react, which is intramolecular now. Therefore, to minimize the polymerization and maximize the cyclic compound, you can take more amount of solvent. That is a technique which is called high dilution technique. There are two techniques, one is high dilution technique, one is template technique. If you can find a template which can hold the reactant in one cyclic fashion, then that helps. Likewise, if you increase the amount of solvent, that also helps. So both high dilution and template technique or one of those can be useful. But high dilution technique, the problem is that reactivity becomes less. Whenever first two molecules has to come and react, they will not come so easily because they are already far apart. Hence, high dilution is not good for reactivity, but we have to compromise sometime. If we increase the concentration, chances of polymerization become high. So, high dilution and template, these are the two basic techniques utilized for making cyclic molecules. Now, the assignment to you is to find out, let's say this is crown ether, a cyclic molecule, and some crown ether are bigger, right? If there are 4 oxygen or 6 oxygen or 7 oxygen, the overall diameter of the crown ether will be bigger and bigger. Likewise, the size of lithium plus, sodium plus, K plus, this ion, lithium, sodium, potassium, etc., their size also keep on bigger and bigger, which size will match to which size crown ether. Wherever size is matching, then that is a good template for preparation of it. Okay. Sometimes size matching itself is not enough. In water, when you do the binding, the lithium or sodium ion, they are not just lithium ion or just sodium ion. Around that water molecule is also there. Wherever the affinity of water with the metal ion is very high, that time the crown ether, when it captures the metal ion, it's not so easy because those water has to be removed. And removal of water is difficult when the binding between metal and the water is high. So compare the diameter or the size of crown ether versus size of alkali metal ion and see which is matching to what. In this chemistry, the bigger one is called host, crown ether is a host, and the smaller one is called guest, potassium ion is a guest. Host and guest is called host-guest chemistry. Heard about host-guest chemistry? So this is called host-guest chemistry. A part of supramolecular chemistry is host-guest chemistry. Do you know the structure of DNA? DNA, there are two strands, double helix strand. Those two strands come together, form a helical thing. And what is the binding between those two strands? Hydrogen bonding. The nucleobase G triple bond C. What triple bond? Hydrogen bond. Right? G triple bond C, A double bond T, which is hydrogen bond. So those complementary base pair, when they come, they form bond. Hydrogen bond is a very weak force. It's not like covalent bond. Right? But number of hydrogen bonds, there are thousands of hydrogen bonds. So together they form force, like a very small force, but multiple number is a big force. So in supramolecular chemistry, the interaction between host and guest is through weak force. What are the weak forces? The hydrogen bonding is one of the things, right? Electrostatic interaction, polar interaction. K plus is cationic, right? K plus is cationic. Oxygen is polar, right? This negative dipole of oxygen and potassium ion, that binding is electrostatic interaction. Electrostatic interaction, hydrogen bonding interaction, even van der Waals interaction. Do you know pi interaction? Pi interaction. So pi interaction can be of different variety. Do you know halogen bonding? Like hydrogen bonding. You heard about halogen bonding? What it is? Yeah, bonding between two halogens. So those of you who do not know halogen bonding, search from some source. Halogen bonding is a weak interaction which happens between two halogen atoms. Which two halogen atoms, what kind of interaction? You search for it. So all these weak interaction, electrostatic, polar, hydrogen bonding, pi stacking, hydrophobic interaction, van der Waals interaction, when multiple number of such interaction comes together, it becomes a strong binding force and host and guest form complex. The simplest possible example of host-guest complex is a host and a guest forming host-guest. H and G forming Hg, not mercury. Okay, H plus G forming Hg, and when it forms host-guest complex, since the binding force is weak in nature, it can dissociate as well. So this process is reversible in nature. Okay. If it is reversible in nature, there will be some amount of host and some amount of guest which are not interacting with each other, and some amount interact, forming a complex. If you take 1:1 host and guest, let's say everything do not form host-guest complex. Whatever part form, the concentration divided by this concentration, that's the equilibrium constant, right? Equilibrium constant. If you take logarithm of that equilibrium constant, it will be a smaller number. The logarithm of this equilibrium constant will be a smaller number. and that is called binding constant. Bigger the concentration of host gas complex, higher is the binding constant. And the binding constant value also depends upon the solvent. In certain solvent, whatever the binding constant, another solvent, it may be different. What you saw now so far is crown ether and potassium ion as host and guest. The guest is cationic. This is cationic. There are some host molecule which can bind anion. What did you say? No, not oxygen. The guest is anion. For example, Cl minus. Cl minus can be a guest where the host is capable of binding anion. There are host molecule which can bind anion. Let's say we have a NH. If I protonate it, it becomes ammonium. Right? It's ammonium. Suppose something else is there. Ammonium is cationic in nature. So if one anion come here, then the interaction between this and this is electrostatic. Plus charge, minus charge. As well, this can be hydrogen bond. Right? So anions are usually bonded through hydrogen bond and through electrostatic interaction. So there are host molecule which can bind anion. There are host molecule which can bind neutral molecule. So look for examples of cation binding host, anion binding host, neutral molecule binding host. There are many. Okay. So this one was prepared by Pedersen and this was prepared by Lane around 1967, 1969. Within 1 or 2 years, he realized the work of crown ether and prepared krypton. Is it possible to draw like that? Just few benzene rings. I have not yet completed. So, in crown ether and krypton, I showed that they are flexible compounds. If I collapse like that, it changes conformation. If it changes conformation, then that requires some energy to come back to the conformation where it binds better. Wherever it doesn't bind, that is the most stable one. And when it binds, that is not the stable one. So it has to pay some energy to come to that binding thing. But if you include rigidity in the molecule, like this one, only it can rotate slightly here, right? OMe, there are everywhere oxygen with a methyl group, OMe. So this oxygen, if it binds to metal ion inside in this area, then the host molecule is now rigid, right? It cannot turn too much. So in that case, binding will be better because it doesn't have to pay the extra energy for coming from that stable to unstable one. It's already in some conformation which require only slight change to bind. They are called spherent. So around the same time, this was prepared by somebody called Crum. So Pedersen, as I told, he already retired from job, just out of interest he was doing something, and Lane just started his career, a new assistant professor. He made that one, and the Cram is somebody who is at the middle of his career, not too young, not yet retired. So he made spheron, and these three people got the Nobel Prize together in the year 1987. So Pedersen prepared in 67, worked for 2-3 years and stopped and forgot everything. After 20 years before he died, he got Nobel Prize. And Lane got Nobel Prize in his early age. And after that, he contributed a lot to supramolecular chemistry. And he is the person actually who driven the supramolecular chemistry, defined this chemistry and created a field. And Cram started something, but he did not continue for too long time because he was already in the middle age. So the contribution of Lane to this chemistry is too big. He has a book. One of the early book of supramolecular chemistry was written by Lane. Supramolecular chemistry, a very thin book having maybe 200 pages or so, that contains a lot of good things, how the chemistry started. And later on, there are books which are very big, thousands of pages, considering a lot of fields developed and so many things happened. So there are a lot of pages, good books are there. But one of the founding book is by Lane because he defined everything in supramolecular chemistry almost. Do you know what is bakelite? Which one? Phenol formaldehyde resin. Phenol formaldehyde. What is that resin? So what is the chemical? Don't show the material. Chemical. As a chemist, what is the chemical structure? Any idea? Can you draw the structure of bakelite or partial structure? Bakelite is known, right? It's a polymeric hard material used in switchboard and so many other purposes. When phenol reacts with formaldehyde in presence of a base, it forms material which is called bakelite, and the structure of bakelite is almost not known. People predict different kind of structure, almost not known. Essentially, the ortho and para position of phenol are reactive towards formaldehyde, forming linkage like OCH2 or CH2O or CH2O, CH2, like that kind of thing. Then it attaches to another aromatic ring and it forms some kind of structure for which you definitely do not know what it is. It can be anything, but whatever it is, the material is so important commercially. It has a lot of material value because it was a very hard material and different kind of things could be prepared, and bakelite was prepared by Bakeland, and that became a company, and they earn a lot of money just because when phenol and formaldehyde mix with the base, it forms something which you do not know, and that become a big commercial success. And this Bakeland is probably in your class 12, you must have seen, right? Somewhere there. So somebody protected one of the site by a tertiary butyl group. So now only 2 sites are available. And then they reacted with formaldehyde under certain control condition by optimizing it. We do not have time to go to those kind of detail. Let me put. I put R at the top and OH at the bottom, something, right? So when phenol substituted at the para position of the bulky group, reacted with formaldehyde in presence of certain base under certain optimized condition. In between, methylene groups are there. And 4 number of such group, then it cyclizes. Okay. So, four number of such group, it goes in a cyclic manner, and it's this side you see is wider, this side somewhat narrow. It's not like a parallel cylinder kind of thing, it's a little bit conical kind of thing. Have you heard about or ever seen this kind of structure? This is called calixarin. Calixarin. It looks like this. Now things are more interesting, right? It's actually like a bowl. You see, each of this group is a 6-membered aromatic ring having a alkyl group there, and at the bottom you see there are OH group, and the OH form hydrogen bonding with O. H of one O hydroxy group and oxygen of the next one form a hydrogen bond. This purple color line is hydrogen bond, and this OH form hydrogen bond with that, this with that, and this with that, and so on. So this hydrogen bonding, 4 number of hydrogen bonding, stabilizes this in a particular area. So this is somewhat like the crown ether now, and it's like a bowl having a space here. So this space can bind neutral molecules. This is called calyx 4 arene. Like 18 crown 6 you say, this is called calyx 4 arene. Likewise, calyx 6 arene, calyx 8 arene, and different kind of calyx arene are there. But calyx 4 arene is the most popular one, which is most studied. So calyx arene is a field which is developed by a professor called David Gutsy. Crown ether, krypton, calyx arene are 3 basic kind of molecules. If you look at any supramolecular chemistry group, you will find it. Although Sferran got Nobel Prize, that is not that much well developed, but that was the early thing. Calyx arene happened later. So in all these cases, the molecule having a space, it's a physical space you can say. So this is the space here. Now this is a pi ring, right? So another pi stacking can happen here. So this bowl can contain some guest molecule. It can bind guest molecule here. It can bind here. When all the 4 things are at one side, it's a cone. If the hydrogen bonding is broken, or instead of OH, if I have OCH3 or OR, then the hydrogen bonding is not possible. If hydrogen bonding is not possible, then it can also rotate like this, right? It can rotate like that. So when it rotates, all the 4 at one side, or 3 one side, 1 is like that, or 2 one side, 2 in the other side. And which 2? The one which is side by side, or one is diagonally opposite. So all possibilities are there. Hence it will have many possible conformations. The most stable one is possible when there is a hydrogen bonding, and this hydrogen bonding is also favored by a certain solvent, not favored by a certain solvent. The calyx arene molecule is one of the well studied molecule having a confined space. Okay. And this is the one which can be actual cap kind of thing you put on your head. Crown ether is the beginning. You can have a look. Okay. So in the macrocycle, what I call macrocycle, the oxygen and carbon atom, they are attached to each other by covalent bonds. The ring formation is through covalent bond and the guest binding is by weak non-covalent interaction. And the metal K plus, instead of oxygen, if I have nitrogen here, which I started at the beginning of the class, I told you, bidentate ligand, tridentate ligand, even tetradentate, I made a cyclic ligand. Those cyclic ligands are nothing but the nitrogen version of crown ether. You heard about porphyrin? What is porphyrin? You find in photosystem, in photosynthesis. It has a magnesium inside. There are 4 nitrogens. That is also a cyclic ligand. Let's say in a macrocycle or in a ring, metal is part of the ring. Instead of metal is bind inside the cavity. If metal become part of the ring, then that is called a metallo ring. Right? It's called a metallo ring. Okay. Another thing I'm forgetting to tell you. You heard about catenan? CATENANA. Okay. There is a bond called mechanical bond, like covalent bond, ionic bond, hydrogen bond. So many kind of bonds are there, halogen bond, pi interaction bond. You heard about mechanical bond. Suppose one ring is there. Let's say this is a ring. And another ring is there which is passing through it. Let's say this is another ring. In the magic, sometimes they attach 2 rings. Have you seen? Let's say one chemical structure is a ring, another chemical structure is a ring, and that ring is passing through the other ring. Then what is the bond between both the rings? Nothing. But still, we cannot separate one ring from the other ring. Such kind of molecules are called catenan. Have you seen the symbol of Olympic? There are 7 rings which are interconnected with each other. One ring is having this kind of connection. It's not attached, but it cannot be removed. Right? So that is called catenan. So there is one field which develop like this called catenan. And if it is catenan, if it is ring, the ring can move. Right? It cannot come out, but still it can move. When there is some movement, if that movement can be controlled, whether it will be positioned here or there, or it will rotate around, all those things is called molecular machine. Molecule when act like machine, when a wheel is rotating or when the gearbox is rotating, this is all motion. So when such kind of motion can be done in a controlled manner in molecule, that is called molecular machine. So the other aspect of supramolecular chemistry, which got Nobel Prize in 2016. In 1987, first Nobel Prize was obtained. In 2016, the next Nobel Prize came. The people who prepare that kind of molecule catenan and molecular machine, where molecule can be controlled and their movement can be controlled from one position to another position by some chemistry. That's called molecular machine, which received Nobel Prize in 2016. Okay, so coming back here, if metal is part of the ring, that's called a metallo ring. So how to make a metallo ring? I started with this ligand which is bidentate, not chelating. Okay. Do you know palladium 2 plus is square planar? PDCl4 2 minus. is square planar. Do you know that? In nickel, it's tetrahedral or square planar depends upon the ligand strength. But in palladium, they are square planar. Right? So palladium square planar means there are 4 binding sites, palladium 2 plus of course. Suppose 2 of the sites are bonded with a bidentate chelating ligand, ethylene diamine. Then 2 more sites are still there. If you put here okay, palladium is 2 plus. Hence, there has to be 2 anions also. Let's say nitrate. 2 nitrate anions. Okay, so here is palladium, here is this bidentate non-chelating ligand. Do you understand what I draw now? There are 4 palladiums and they are square planar. 2 sides are by bidentate chelating ethylene diamine and the other 2 sides by bidentate non-chelating. Right? It forms a square kind of compound. This is called a molecular square. And of course, there are 8 nitrate. There has to be 8 nitrate because there are 4 palladium. Right? This is called molecular square. This was prepared in the year 1990. So now compare the crown ether. It is a cyclic molecule having a space inside and all the bond within the cycle are covalent. Now when metal is part of the ring, everything is not covalent now. The bond between metal and ligand, this is not covalent. They are kind of having some covalent character, maybe non-covalent. If you break a carbon-carbon bond, the molecule is broken. But if you break a metal ligand bond, it is not broken. It can again form. Metal ligand bonds are reversible in nature. If it forms a bond and it can dissociate, again it can form. If you remember M plus L, ML, ML plus L, ML2, like that ML6, beta 1, beta 2, do you remember something? Stability constant. So in that way, metal ligand bond can form, can break. So this is a new kind of host molecule where metal is part of the ring. And since metal is part of the ring, usually the overall charge of the ring is cation. And the space inside is good for binding guest molecule. Just think if you do not have your ethylene diamine. This molecule now I draw like this is the miniature drawing for that one. Okay. Now just imagine if I do not have the ethylene diamine around here, then what would have happened? It would have continued like this, right? Like that it will continue. So that's a polymer. That's a polymer which is called coordination polymer. You know polymer. Whenever metal is part of the polymer, it's called coordination polymer. And the coordination polymer, what is shown here is like 2-dimensional. This is a 2-dimensional molecule. If this metal center is octahedral in nature, and 3 sides are protected, then we could have done one more from here, right? If it's an octahedral metal, 3 sides are protected by diethylene triamine, and 3 sides are available which is 90 degree to each other. They are facial and meridional isomer. In an octahedral, if 3 sides are facial or 3 sides are meridional, in a facial manner, it's possible to make a cube here, right? This is 3-dimensional. Likewise, it's possible to make cube here in 3 dimension. They are called metal organic framework or coordination polymers. So at present in supramolecular chemistry, this is one of the field which is likely to get Nobel Prize possibly in next few years, which many people are predicting. In supramolecular chemistry, if a Nobel Prize is to come, that may be the area. So crown ether, krypton, sphaerant, calyxarine, these are the name roughly is registered in your mind now, right? And in supramolecular chemistry started like that, and mostly it's like host guest binding, and the behavior of the guest inside the host molecule is different from the behavior of the guest when it is outside. Okay, so many kind of things are done at molecular level in supramolecular chemistry. Okay, so I do not have a model for this kind of thing. I have already so many atoms there. If I want to teach, then there is no end to it, and you will be bored, and that may not be very effective. So if you want to build up by yourself, now we have got some introductory idea, and you can check that CSIR syllabus, supramolecular chemistry is a part of it. For that, crown ether, krypton and calyxarine are kind of topic which you should read from some books. What I finish in few minutes, but you have to read several pages, several hours to understand this chemistry if you want to score some more mark, or if you are interested in knowing this field in future. Okay. So shall we take a group photo with all this model holding? Some of you can hold it. Come this side. Whoever want to hold whatever, hold it. Stand here. We'll ask somebody to take a photo. Come. Come with your notebook or model or whatever. We can stand here. We'll ask them to make a photograph. Whoever can capture whatever molecule that belongs to you for the photograph. After that, do not forget to return it. Okay. Whenever you stand, let people come. When people come, automatically. Raja, take a photograph with the cell phone. That camera can be switched off now. Switched off. It's over. Raja, take this. You have a steel
SwayamPrabha, Digital India, Educated India.